Hi, my name is Peter Baddoo, and I'm an applied mathematician at the Massachusetts Institute of Technology. And today I'm really excited to share my recent research on kernel learning for robust dynamic mode decomposition. And this is a collaborative work between myself, Benjamin Herrmann, Beverley, McKeon, and Steve Brunton. And our paper is available on the arXiv. It's called Kernel Learning for Robust Dynamic Mode Decomposition and the Linear and Nonlinear Disambiguation Optimization, or LANDO for short. And to motivate the LANDO framework, I want to briefly recap two of the leading methods in data-driven dynamical systems: the dynamic mode decomposition, DMD, and the sparse identification of nonlinear dynamics. The dynamic mode decomposition seeks to find a low-rank linear operator that best maps data measurements forward in time. So for example, in this example of the vorticity flow, the vorticity field for flow past a cylinder, DMD determines this matrix A that advances measurements of the vorticity forward in time. It maps x of k to x of k plus 1. And DMD has been very successful for a variety of fluid dynamic systems, partly because it works well with high-dimensional data, which are typically encountered in simulations and experiments. However, DMD struggles when there are nonlinearities involved in the system. Because DMD is finding a best linear fit, it cannot capture the quadratic behavior of this data over here. On the other hand, SINDy works very well for nonlinear systems, but struggles with high-dimensional systems due to the computational complexity of the underlying algorithm. So here, SINDy is identifying the Lorenz system, and it can build a great nonlinear fit to this data from which you can obtain local linear models. But it's difficult when you have a large number of variables, like in this example here. So how can we take the best of both of these systems? How can we obtain interpretable linear models from dense, high-dimensional, nonlinear systems? And in particular, how can we extract the roles of linear and nonlinear mechanisms to better inform stability analyses, control, resolvent analyses, and achieve other engineering tasks? So that is the aim of LANDO. The aim of this project is to develop a machine learning method that efficiently separates or disambiguates the roles of linear and nonlinear mechanisms when the data is both high-dimensional and nonlinear. And using LANDO, we're going to be able to analyze all these different systems, ranging from dynamical systems to partial differential equations. And from these data measurements, we're going to be able to extract the underlying linear operator and also nonlinear forcings that excite that linear operator. So more on this figure later. But in order to present LANDO, we need to take a slightly different perspective on traditional representations of dynamical systems. So the traditional perspective, and this is how SINDy and related algorithms work, is by representing our dynamical system, represented by the function here, f, as a linear combination of features. So we have this matrix multiplied by this vector of features, phi. And typically, we might take the features to be polynomial functions of our state. So if we have a state with n entries, we can take those entries and then also compute some polynomial functions of those entries, and so on and so forth up to order d monomials. And then there's this transition matrix that relates those features to outputs. So for example, with the Lorenz system, the state dimension is 3. We have x, y, and z. And we would represent that dynamical system in this matrix form. So here we have the linear and quadratic features of your state, and then this matrix maps those features into velocity measurements of x, y, and z. But this approach becomes very challenging when we have high-dimensional feature spaces. So for example, if we wanted to construct a feature space consisting of degree d monomials when the state is of dimension n, then we would construct features of this form. But the dimension of these features is very large. It's this number, capital N, which scales combinatorially. So the curse of dimensionality becomes very important when we have a large number of features and a large number of states and nonlinearities, and that generates a very high dimensional or even infinite dimensional feature space. So our way around this is to not construct these features explicitly, but construct them implicitly through use of a kernel function. And kernel methods is a very developed area of statistical machine learning. Originally, it arose from integral equations. But the basic idea here is instead of representing the function as a linear combination of features, we represent it as a linear combination of kernel functions. So this k represents the kernel function. You can see it takes in two inputs, xi and x here. And then to represent our dynamical system, we need to know what w's we should choose as the weights. These xi's are just the samples, or a subset of the samples of the measurements we have for our system. That's guaranteed by the representation theorem, so all that remains is for us to determine these weights. I'll talk more about the kernels themselves in a little bit, but here are some typical choices: a polynomial kernel or a Gaussian kernel. And then our dynamical system is represented in this matrix form, where there's this big weight matrix here that maps the kernel evaluations onto the function outputs f. So how do we learn that function? How do we learn the weights of the kernel? Well, as in any data-driven method, we need measurements of our system. So this is the typical representation of the measurements in data matrices. So we'd have a system, for example, this flow passes cylinder, and we'd sample it at a number of points in time. So here we have m samples, and x represents the state. So we would construct a matrix of these measurements x, and then also a matrix of measurements of y. And y can represent a variety of quantities. Here we mainly consider that y could be the time derivatives of x, or it can be x advanced forward one step in time. In any case, the system we're trying to learn is this function f that maps x's into y's. And it really doesn't matter whether they're velocity measurements or they're advancements forwards in time. So the typical explicit model will represent this, the model in this form, and then the minimization problem is to find this purple matrix that best reconstructs the system in the energy sense. So this is the Frobenius norm, and this is minimizing the reconstruction error in energy. But as we mentioned, this big number, capital N, can become very large so that this optimization becomes intractable. And in any case, you wouldn't be able to evaluate your model if n became too large. So instead, we represent it in this kernel form that I mentioned previously. And we're basically making a trade here. We're trading capital N for n. And m, remember, is the number of samples. This little n is the dimension of the state space. So here are some key references on kernel methods. One I particularly want to point out is this one, which presented the kernel recursive least squares algorithm. Because this problem is an improvement over the previous problem, but it's still quite challenging because this matrix, this k x of x, can be very large if we have a large number of samples. It can also be ill-conditioned. So to get around that, we adapt to get around the computational issues associated with that, we adapt the kernel recursive least squares algorithm to build a dictionary of samples that most significantly contribute to the dynamics. And then that allows us to reduce our system to a much smaller one. So you can see this matrix that we're trying to learn, the matrix of the weights, it's much smaller than previously. Here it's n by tilde m, where tilde m represents the dimension of the dictionary. And now this minimization is very computationally attractive. I'm going to film a separate video on the dictionary learning so you can find more details there. The question of how we design a kernel is really important in this system, in this framework. And there's actually two dual views. So one view is that we take our knowledge of the physics of the system and we use that to design the kernel to model the system that we're studying. So if we're studying the Navier-Stokes equations, then we want a kernel that can account for nonlinear quadratic interactions between states. So in that case, we would use a quadratic kernel because that has precisely those features. On the other hand, we might have no intuition about the underlying physics of the system, but we want to learn the physics through a variety of kernels. So we would try the LANDO framework on a bunch of different kernels, and then through cross-validation, determine which one performed the best, and then that could give us some insight about the type of physics going on in this system. And there are many other principles for designing kernels. Here we have some physical properties, such as the type of nonlinearity, symmetries, whether there's bias, and then this explains how we can incorporate those physical properties into the design of the kernel. So these specify the form of the kernel. Learning the hyperparameters of that kernel is a separate issue that we don't go into here, but there are sophisticated methods for dealing with that. So once we've chosen our kernel and we've learned the weights of that kernel, an important question is, how do we interpret the resulting model? Because this is an implicit model, so it's not clear what it's actually told us. Like, what physics has it uncovered? What mechanisms does the model think is important? And we're particularly interested in understanding the linear mechanisms in this system. So we want to take our dense, opaque, uninterpretable model and extract the underlying linear operator. And to do that, we take our model, which is up here, and then we can express it in the following form. Express f as a linear function of x plus some bias plus a nonlinear function. And this x prime represents fluctuations about some base state. So when you're looking at something linear, we need to know linear with respect to what. So you take some base state, which could be an equilibrium solution of your system, or just zero, or a statistical mean, and then you look at fluctuations about that. And these need not be small fluctuations, and we can always express our system in this form. And actually we find that for a huge variety of kernels, like almost any kernel you could think of, the linear operator takes this very neat form. It's automatically factorized into three matrices: the weighting matrix, the adjoint of the dictionary matrix, and then a diagonal matrix, which represents the effect of the base state that we selected. And then given this operator, we can now do diagnostics on the linearization. So we can do a dynamic mode decomposition. That is, we look at the spectrum of this linear operator and the modes. And we can also do data-driven resolvent analysis. We can look at the resolvent operator of this linear component and look at its singular value decomposition. So this step enables us to take our opaque model and then interpret it through the lens of linear and nonlinear mechanisms. And this is a summary of the framework, of the LANDO framework. As is typical in data-driven methods, we begin by collecting data. This is from the KS equation, which we'll talk more about later. We then arrange the data into these matrices. We select a kernel function based on experiment, intuition, physical knowledge, or cross-validation. Then we build this sparse dictionary of samples that contributes substantially to the dynamics, and then perform regression on that dictionary, and finally extract the model. And one of the really cool things about this approach is that it works completely online. So that was one of the great contributions of the original kernel recursive least squares paper, that it is an online algorithm. So if your data is only available in streaming format, or it's too large to store on your computer, well, you can bring in each sample one at a time and then iteratively update and refine your model as that new data becomes available. So this figure shows the effect of LANDO applied to a variety of systems. So here we have some dynamical systems and then some partial differential equations along the bottom. And we're comparing the linear operator that is learned by a standard application of dynamic mode decomposition, which doesn't account for nonlinearity. And then in the middle, we have the exact linear part, or the truth, the ground truth here. And then finally on the right, we compare the linear part learned by LANDO. And you can see that the performance of LANDO is much better than standard DMD. And in particular, for the PDEs, LANDO extracts this strongly banded structure. So it's the diagonals are really emphasized, because this is a partial differential equation, so we expect spatial locality, of which the matrix interpretation is this diagonal structure. And something else that LANDO gives us is the nonlinear forcing. So on the far right, we have LANDO's predictions for the nonlinear component of the data, and you can see it's really cleanly disambiguated that linearity and nonlinearity. And of course, exact DMD doesn't have anything to say about the nonlinearity because it's not modeled. So as an illustrative example, we applied this to the Lorenz system, which is a typical model of chaotic system. And along this top row, we have the training data here. And later we'll see reconstructions of LANDO. And here we have some predictions. And then along the bottom row, we have the local linearization of the model about the base state at this point, x bar. So this is an equilibrium point of the Lorenz system. So the norm of f there is 0, and then this is the linearization and the eigenvalues. So to begin, we apply LANDO with a linear kernel, and we wouldn't expect LANDO to perform well in this situation because the dynamics are fundamentally nonlinear. So this is what exact DMD would give you, and we'll see that DMD is biased by the nonlinearity. Of course, the reconstruction is very poor here. It can't reconstruct any of these dynamics. The prediction is also poor. In terms of the linearization, it does actually identify the top row of the linear model accurately, because there the dynamics are truly linear. But then the other two rows are quite off, and then so the eigenvalues. Now if we apply a Gaussian kernel, we have a great reconstruction of the dynamics. The prediction is qualitatively good, but it's not quantitatively that good. And then LANDO does identify this x bar as an equilibrium. So this is 10 to the minus 3, so it thinks that the dynamics are basically stationary there. And then it also learns a relatively accurate linearization around that base state. And you can see the eigenvalues are somewhat in agreement. But then if we apply a quadratic kernel with LANDO, it really nails all of these attributes. So we have a great reconstruction, a great prediction, and a solid identification of the equilibrium point, including the eigenvalues. And this shows that the quadratic kernel was the right one to choose. And we know that already because we know that the dynamics of Lorenz are quadratic and linear. But if we didn't know that, then this analysis would show us that there is a very strong possibility that this system has underlying quadratic dynamics. We also apply this to the Burger's equation, which is a canonical model for turbulence, one of the simplest models, given by this PDE here. And we want to uncover the linear part of the spectrum of the Burger's equation purely based on data measurements. So in yellow, we have LANDO's predictions. In gray, we have the true values of the eigenvalues. And then blue is what DMD suggested. And you can see that LANDO really nails them, even though this system really has a very small linear part. LANDO can still efficiently extract that linearity. We also tested it on the KS equation, which is the simplest chaotic partial differential equation. And here, we were again able to extract the linear component of this operator, which is buried beneath a lot of nonlinearity and chaotic behavior. And we were able to extract the linear part of it's rather intricate part of the spectrum down here. And this was all done very efficiently using these kernel methods. And then the last example, which I think is really cool, is an example of learning underlying physics from a high-dimensional nonlinear system. So this is the Kuramoto model of synchronization, given by this equation with some forcing. And it represents how states can, how a coherent structure can emerge through synchronization. And the question is, given these measurements of the synchronized system, can we learn the natural frequencies? So can we learn this omega for each of these oscillators? So that's what would happen if there were no coupling between them. And what we find is that if we apply LANDO with this kernel, which is a nonlinear trigonometric function, we get a great prediction or great reconstruction of what LANDO thinks the natural frequencies are. So you can see this is just a subsample of 2,000 oscillators, and it has less than 1% error on average. So to sum up, we've presented a data-driven kernel method called LANDO, the linear and nonlinear disambiguation optimization, that robustly extracts dynamic modes from nonlinear dynamical systems. And one of the advantages of LANDO is that it removes some of the bias that standard linear dynamic mode decomposition has when there are nonlinearities involved. And by implicitly modeling those nonlinearities, we can extract the true linear operator that generated the data. And given that linear operator, we can perform a separate dynamic mode decomposition, or we can perform resolvent analysis and look at the spectrum and look at the singular values. And through the use of kernel methods, this method scales very well to high-dimensional, even infinite-dimensional nonlinear problems. So the arXiv paper is available here, and I would love to receive any questions, comments, or suggestions about this work at my email there. Thank you for listening.